This is problem number 19 from chapter 36 of the Survey-Jewett text we use in class. We're told that we have an object in front of a concave spherical mirror. We're told that it is 0.6 meters away from the image that the mirror produces, and we're told that the image is 4 times the size of the object and it's inverted, and we're asked to find the focal length of this mirror. So we've got a couple of relationships we can exploit to figure out this problem. The first is the magnification. We know that M is equal to minus Q over P in general. And let me make that P look a little bit better. In this problem, we're told that the magnification factor is 4 and that the image is inverted, which means we put a negative sign in front of the 4. So now we have a relationship between the magnification factor, which we know, Q and P. I can solve this, and I get that Q is equal to 4P. Negative signs are going to cancel. I can solve that for Q in terms of P. I could also solve it for P in terms of Q. I'm going to do it this way, though. So that's one relationship we have. We're also told that the distance between the object and the image is 0.6 meters. Just from looking at this picture, from the geometry, from the way we define Q and P, P is the distance from the object to the principal focus point, or the point of intersection of the principal axis and the mirror, I should say. Q is the distance from the image to that same point, and we are told that the distance between the object and the image is 0.6 meters, so I can immediately form, just from the algebra, Q minus P is equal to 0.6 meters. Right? So I can solve that now. Well, I can substitute in what I know the value of Q is. I've got 4P minus P is equal to 0.6 meters. If I run through this, I will get P is equal to 0.2 meters. All right. So that was the whole idea of forming the first relationship between Q and P, is that I now then use the geometry of the system to determine an actual value for P. Okay, so I still don't have the answer to the problem. I'm looking for the focal length of this thing. So now what I can do is use the mirror equation. I go to a new sheet. I know that the focal length of a mirror is equal to 1 over P plus 1 over Q inverse. Right? So now I can again substitute in my value for Q. Recall, I solved for Q here as Q is equal to 4P. So now I can form that here. 1 over P plus 1 over 4P. And again, I'm going to have to take the inverse. Okay, if I do this, I get 5/4 P is equal, 5/4 P inverse, and let me do that a little bit cleaner. P is actually in the denominator here. 5 over 4P, I should say, is equal to the focal length of the mirror inverse, which means, of course, that the focal length is 4/5 P. P is then 0.2 meters, so I can form this 4/5. 0.2 is 1/5. That equals to 4/25 meters. This should be meters. Alright. So what does that look like? Let's go to our new slide. Here's my mirror. Here's my principal axis. And I got, here's P. There's my object. Here's P. 4/5 of P would be approximately right there, just eyeballing it. Right. So you can see what's happening. If I do the rays, let me go to a different color. We do the ray from the top of this object. It's going to strike the mirror like this, bounce off, go through the focal point, and the bottom ray, let me do that in a different color. Remember, we need two rays to for a ray diagram to determine focal points is going to just look like this. And so what I get out of that is an inverted object four times with a magnification factor of 4. Okay? The rays will pass through the focal point. That's the important thing here, and that's where I get my inverted image. It's inverted because of where the focal point is relative to the other points. So just as I should also point out that this image is real because it's on the same side of the mirror as the object. And another way to think about it is light rays can actually exist in this space, so that means the object is real. Okay, for the next part of the problem, we're asked to do the same setup, only this time with a spherical convex mirror. So I've drawn that situation here. We're still given that the distance between the object and the image is 0.6 meters. We can, just because we know how convex mirrors work, we can immediately say that the image is virtual. Light rays can't actually exist inside the mirror, so the image is going to be virtual. This time we're told that the magnification is 0.5 and that the image is upright. So my magnification is still equal to minus q over p, only in this case it is 0.5 and it is upright. The image is upright, so it's going to be positive. Again, I can solve this for q in terms of p. I get that q is equal to minus 0.5 p. No problem. From that point, I can again form the mirror equation. Right? I've got that the focal length is equal to 1 over p plus 1 over q inverse, and I can substitute in my value for q. I get the focal length is equal to 1 over p minus 1 over 0.5 p, and that is an inverse. And if I run through the math there, I get that this is just equal to minus 1 over p inverse, which means, of course, that the focal length is just equal to minus p. Okay, let me go to a different page and do that. Focal length is equal to minus p. Let me go back. I also have a relationship between p and q. I've got sign conventions to worry about here because q is on the inside of the mirror. So I've got to remember that q is negative. So what I have here now is that p minus q is equal to 0.6 meters. It's minus now because of a sign convention. Q is on the inside of the mirror. Okay, so what I can do at that point, I can resubstitute in my q value for p. Q is minus 0.5 p, so I get p minus 0.5 p. It's equal to 0.6 meters. Of course, that works out to be 1.5 p is equal to 0.6 meters. That means p is equal to 0.4 meters, which means, of course, that my focal length is equal to minus that, minus 0.4 meters. That's the answer to my question. Let's see what that looks like. Sorry, that's from an earlier video. Here I have my convex mirror now. Let me draw the principal axis. I've got my object. I've got my image. So let me draw some light rays. The one from the tip. It's a convex mirror now, so this will go outward. If I then trace it back, I find that it intersects there. Change color again from my other light ray. This one will reflect straight backwards because it's intersecting, or it lies along the principal axis. So if I trace that then back, I get something that looks like this, and that's where the image comes from. Okay, hope that made sense.